tiny quantum computers capable of performing calculations 100 million times faster than conventional computers have already been made. But scientists are having trouble scaling up these systems to a useful size for applications such as artificial intelligence. Now scientists have developed the first ever quantum bridge, which could link lots of small quantum computers together. The discovery opens up the potential to create more powerful AI systems through the development of quantum computing. Quantum computing takes advantage of the ability of subatomic particles to exist in more than one state at any time. In traditional computers, data is expressed in one of two states, known as binary bits, which are either a 1 or a 0. But quantum computers use quantum bits, or qubits. Computations in a quantum computer occur when qubits interact with each other. Therefore, for a computer to function, it needs to have many qubits. One of the main reasons why quantum computers are so hard to manufacture is that scientists still have not found a simple way to control complex systems of qubits. But the researchers behind the new quantum bridge say it would overcome this problem by linking small quantum computers instead of just building one large one. People have already built small quantum computers, said Ryan Camacho, researcher at Sandia National Laboratories in Carlsbad, California, and leader of the research. Maybe the first useful one won't be a single giant quantum computer but a connected cluster of small ones. The new bridge is created by adding impurities into diamond. The work, which was joint with Harvard University, used a focused ion beam implanter at Sandia's ion beam laboratory. The beam is designed for blasting single ions into specific locations on a diamond substrate. The researchers replaced one carbon atom in the diamond with one silicon atom, which causes the carbon atoms around the silicon to flee. This leaves the silicon atoms with a lot of space, and even though they are in a solid material, they behave as if they are in a gas. What we've done is implant the silicon atoms exactly where we want them, said Camacho. We can create thousands of implanted locations which all yield working quantum devices because we plant the atoms well below the surface of the substrate and anneal them in place. Before this, researchers had to search for emitter atoms among about 1,000 randomly occurring defects, that is, non-carbon atoms, in a diamond substrate of a few microns to find even one that emitted strongly enough to be useful at the single photon level. When the silicon atoms are settled in the diamond substrate, laser-generated photons bump silicon electrons into their higher atomic energy state. The electrons return to the lower energy state because all things seek the lowest possible energy level. When this happens, they spit out quantized photons that carry information through their frequency, intensity, and the polarization of their wave. Harvard researchers performed that experiment as well as the optical and quantum measurements, said Camacho. We did the novel device fabrication and came up with a clever way to count exactly how many ions are implanted into the diamond substrate.